Hi everybody, it's David Porter, and I want to talk about the scientific method and experiments, which are a essential part of the scientific method. The scientific method is a set of procedures to gather information, analyze the information, and draw a conclusion. The process of the scientific method begins with a theory. A theory is a very broad, general framework for ideas. You take a piece of the theory and phrase it as a question. This is a hypothesis. And what we want to do with an experiment, utilizing the scientific method, is to find evidence for or against the hypothesis. A good scientist, a good researcher, is going to be very skeptical. They, of course, want to find evidence for their hypothesis, but in what's called testing the null hypothesis, a good ethical researcher, a good ethical scientist, someone who's conscientious, is going to try to prove themselves wrong. They have this great idea based on probably naturalistic observation of, their environment, ideas that they've generated through contemplation or reviewing the literature that is the research that's available, and they've drawn some conclusions. So of course they want to prove their hypothesis, but they actually have to work hard to falsify or disprove their hypothesis. How do we do this? One method is an experiment. So to test the null hypothesis, to try to find evidence for or against your hypothesis, and for or against the theory that the hypothesis is a part of, you're going to do an experiment. You need two groups for an experiment: an experimental group and control group. You need at least 50 subjects, and that's the bare minimum. 500 is much better. 5,000 is even better. You get numbers above 5,000, you're going to start losing. You're going to start having trouble with the return on your investment. In other words, you're going to start encountering problems that override the benefits when you get into studies of around 5,000 or more. So you certainly do have studies that are larger than that, using a larger number of subjects. 500, 5,000 is going to yield some very good results. So you divide your subjects into two groups. The experimental group is going to receive what's called the independent variable. You're going to give them something. The control group is not going to receive the independent variable. They are going to get a placebo, something which looks like, smells like, tastes like the independent variable, but it's not active. It's neutral. It doesn't do anything. One easy way to think of the independent variable is it's the input into the situation. That's all it is. The independent variable is the input. And you're going to run the experiment with your subjects, and then you are going to have all this data. So now you're going to crunch the data, you're going to examine the data, and the data is called the dependent variable. That is just the outcome. Independent variable is input, dependent variable is the output or outcome. So you're going to, more specifically, the output. We haven't reached an outcome yet. So you're going to take all this data, you're going to analyze it, and you're going to see if there's a statistically significant difference between the control group and the experimental group. Then you're going to make a definitive statement. Yes, I have found evidence to support my hypothesis, or no, I have not found evidence to support my hypothesis. Then you're going to publish an article in a professional journal. Your peers are going to review this article for clarity, for accuracy, and to see if it contributes to the knowledge base. If so, it gets published. And yes, it's actually way more complicated than that. This is the simple version, the overview. And other scientists, researchers, clinicians, practitioners are going to read this, and then hopefully, if this is a big news, they are going to be interested enough to replicate the experiment. They're going to do your experiment over again, and maybe with a larger number of subjects. They're going to make some adjustments and refinements, do things a little bit differently in an effort to replicate the results, and by doing that, hopefully increase reliability. I almost said increase liability. Boy, there's a Freudian slip. You don't know what a Freudian slip is. More about that later, and another time. You want to increase the reliability, and then the process starts all over again. That theory is refined. New hypotheses are formed, and researchers will do additional experimentation. And over time, this adds to the knowledge base. This adds to the understanding and improved methods in the profession. So this is a long process, and it's a fluid and dynamic process. It's important to think of science as a river, not a rock. A scientific finding is made, and it must be continuously challenged. It's going to change over time and be refined. What we believed 50 years ago is probably going to be very different than what we know today, because we found so much evidence for it, or no evidence for it, or evidence in opposition to it. Okay, quick example. Here's a hypothesis. Drinking coffee helps you study better. So how are we going to do this? We need to do an experiment. Let's get 100 students in whatever field of study. Let's keep it simple and say 100 psychology students. And we're going to give all these psychology students a standardized test of knowledge in psychology. Multiple choice test about basic principles in psychology. Group A, let's say 50 students, that's the experimental group, they're going to get a delicious double espresso. Please don't call it espresso, it's espresso. Espresso. You are going to give 50 students a double shot of espresso. You are going to give the control group, you're going to give 50 other students a double shot of decaf espresso. They're all going to take the exact same test, and now you're going to look at the test scores, and not as individuals but as a group. Did the students in group A, the caffeinated group, doing the double shots of espresso, score higher, get better grades than the decaf group? If so, you found support for your hypothesis that caffeine improves study test scores, concentration, retention, memory retrieval, whatever it is, whatever the details of your hypothesis was. Now we have a couple of refinements we need to make, a couple other points to make. You don't want to do anything to lead your subjects in one direction or another. So that's called the placebo effect, and we want to compensate for the placebo effect. How do we do that? This particular study would be double blind. What that means is nobody knows, none of the subjects, who are the subjects of the research, the students in this case, are going to know whether they're getting caffeinated espresso or decaf espresso. So that's blind number one. Blind number two, or the double blind, is the researcher doesn't know who is getting regular espresso or decaf espresso. A research assistant is going to make the coffee and assign the different cups an alphanumeric code that only they know to indicate which is caffeinated, which is decaf. And you're going to have 100 students. You give them their I almost did it. Espressos. They drink up, they take the test. The researcher is not going to know which group got what until after the experiment is done. This prevents the researcher, or whoever is having direct contact with the subjects, from giving away any nonverbal cues that could influence the outcomes. So that is an example of an experiment. Everybody, thanks for watching, and please hit subscribe and be safe.